My name's Ryan. I'm a NASA Globe Clouds intern and Sat Core intern for the summer of 2021, and I'm going to be going over my research on the solar terminator problem. Bill said a little bit about me. I am a junior at the University of Maryland, pursuing a Bachelor's of Science in Information Science, and I'm also a mentor for the cloud computing stream through the FIRE program at Maryland. And what the FIRE program allows undergraduates to do is conduct research as an undergraduate, and I'm conducting atmospheric science research and computer science research through the cloud computing stream. And currently I'm mentoring students who are within the stream while also conducting research. And this is my first year as a NASA Langley research intern. So the outline my presentation is going to follow is I'm going to first go over the background, and then data sets, approach, and results. And then at the very end, I'm going to have a couple slides for conclusions and future work. So first, to start with the background. My focus of the study is to explore the use of citizen scientist observations in order to validate geostationary cloud detection capabilities during the terminator. And in order to validate the cloud detection capabilities, the NASA Globe Cloud team launched a program where citizen scientists can record observations of cloud coverage near sunrise and sunset. And if you don't understand what this means, that's completely fine. I'm going to dive into the details of what I just said. So first up, the solar terminator problem. What is it? So the terminator is also known as the twilight zone, and it's the line that divides the light and the dark side of the Earth. As shown in the figure here, this is the terminator line. And what's the problem with it is that cloud signals from the terminator can be very hard to interpret, and that's due to very low levels of light. It's not completely dark and it's not completely light on this line, so that makes it challenging for satellite retrieval algorithms to accurately detect cloud cover. So how do we solve this? So both the NASA Sat Core team and the NASA Globe Clouds team offered solutions in order to help solve this problem. The Sat Core team devised an approach that utilizes machine learning in order to help improve cloud detection during the terminator. And then the NASA Globe Clouds team, they launched an IOP, which is an intense observation period that started March of 2021, where citizens could use the Globe Observer app in order to measure the cloud coverage from where they are located. So what the Globe Observer app allows citizens to do is contribute to different problems that NASA needs help solving. So for this specific one, during the terminator hours, citizens could go outside and they would be prompted to take photos of the clouds from the 4 cardinal directions as well as up and down. And they would report variables such as cloud cover, sky visibility, and cloud type. And this data will then allow us to validate the new NASA Sat Core algorithm. So NASA Sat Core is a team, but it also stands for the Satellite Cloud and Radiative Property Retrieval System. So this is a global meteorological satellite data and processing and visualization system with real-time capabilities. And it consists of 5 geostationary satellites. So as shown on the figure here, there's the GOES 15 satellite, which has since been replaced by GOES 17, and it covers the Pacific Ocean. The GOES 16 satellite covers North and South America. Mediasat 11 covers Africa and Europe. Mediasat 8 covers Western Africa, India, and Asia. And then the Himawari satellite covers Australia, the Pacific Ocean, and parts of Asia as well. So this figure we're looking at is measuring cloud top height. And that's what you're seeing in the figure is one of the cloud properties. And this bottom panoramic image is using all 5 of these geostationary satellites in order to produce this imagery of cloud top height. But along with cloud top height, there are other variables that are derived from SatCore, and that includes thermodynamic phase, location, and size and density of the cloud particles. And this is important because the Globe Clouds team uses these cloud properties in order to assist their observations for citizens. So detecting clouds from satellite imager data. Satellite imagers are radiometers, and they have various spectral bands in order to scan the Earth from space, and they measure skin temperature as well as amount of reflected sunlight from the scene below. Now, these two data points are very important because the skin temperature and the amount of reflected sunlight are both used in order to determine if a pixel is clear or cloudy. So we then apply computer algorithms to this data in order to determine that, as well as deriving various cloud properties that I talked about earlier. So then a cloud mask algorithm will then be applied to that in order to determine if the pixel is clear or cloudy. And this is also known as the expected clear sky condition. So when the skin temperature and the solar reflectance are of a certain value, then we can assume that the skies are clear. But when these two values differ by a certain margin, we then assume that the pixel is cloudy. So when there's uncertainties in these data points, that makes for false cloud detection in the scene. So uncertainties in this ancillary data are amplified during the solar terminator. So it makes it very hard to detect clouds when the terminator is passing through. So how do we validate cloud detection? So we know that there is false cloud detection, but how do we validate it's there? And then how would we validate this new algorithm that we're trying to solve it with? The first step would be visual inspection of the satellite data. This includes animations such as RGB animations and cloud phase animations, which we'll look at later. And essentially, it shows you an animation of what the cloud coverage is, and you can physically look at it and try to detect and see if you see any false cloud cover. Another way to validate this is through ceilometers, and I'll touch on this later, but essentially ceilometers are lasers used to measure cloud cover and cloud height, and they're very accurate with low and low to mid-level clouds, but the higher altitude, the mid to high altitudes, it's not the best at detecting clouds with. But you can use this to validate cloud detection from satellites. There's also satellite radar and LiDAR. It's very accurate, but for my project, it wouldn't be the most useful because usually during the terminator, it's not overpassing where the terminator is at, and it also has very low spatial coverage. So it covers about 1 kilometer of surface area. And then the fourth way that we could validate cloud detection is through human observations. That includes the Globe Citizen Science data and a special terminator observation period that the Globe Clouds team is conducting. So we can use human observations in order to validate what we're seeing from the satellites. So now I wanted to give an example of the solar terminator problem. So this graph on the right here, we're looking at the Sahara Desert, and what it is essentially showing is the monthly mean cloud fraction from hourly analyses. So why the Sahara Desert is so good is because usually there's very low cloud cover, if any, over this area. So when the terminator is passing through, it'll bring with it a lot of false cloud detection. So it'll be easier to see because normally it's clear skies over the Sahara Desert. So as you can see in this area, there are these sort of lines of light blue, like light blue diagonal lines as they cross through the purplish bluish area. And what this is when the terminator is passing through the Sahara Desert. So I mentioned this is an hourly analysis. So essentially, this line here would be the first hour, the next would be the second and third. And this really shows that the terminator line is bringing with it approximately like a third of false cloud detection through the Sahara Desert. And the reason also this example is so I would say like amplified is because there's a lot of surface temperature inaccuracies over this geographic area. So now I'm going to look at an animation. This is a cloud phase animation, which we can use to validate cloud detection from satellites. Some quick important notes is that green means clear skies. Yellow is a weak cloud signal. You can see some yellow there. Blue is low liquid cloud detection, and then the red means high ice cloud detection. So essentially, anything that isn't green is some form of cloud detection. So if I go through this animation, I'd like to point your attention to the right side of the screen. You can see sort of a faint line going from the North and South Pole. And as it traverses the globe, it brings with it a band of false cloud detection. So this is the terminator line, and all of the false cloud detection it's bringing with it is causing problems in these figures. So you can see, and then eventually it'll traverse the whole globe and bring with it a lot of false cloud detection that we want to clear up. Now I wanted to talk about an example in the United States. These examples are a little harder to see than the one we just looked at. However, it's still very present within North America. So the reason we're looking at this is because a citizen scientist alerted us of this case. The citizen scientist location is in the center of Oklahoma, represented by the pink square. And on the left, you have the RGB animation, and on the right is the cloud mask product from SATCOR. So this is going to be a sunrise case. As you know, the left side is dark and the right side is lighter. And as the Terminator comes through, you're going to notice in the Midwest a ton of false cloud detection, because again, blue means clouds and green is clear. And you can see a lot of false cloud detection in the Midwest in our cloud mask here. Where in the RGB animation, there doesn't appear to be much of any. And what really reassures us that this is false cloud detection is then as the Terminator passes through, it clears up again. So you're going to see as the Terminator line passes through, the Midwest then clears up and is back to normal. So what is my goal with this project? So what I want to do is I want to find as many cases of the GOES 16 and GOES 17 satellites falsely reporting cloud cover during the Terminator. And if you remember, those are the two satellites that sort of cover North America, where we get most of our citizen scientist observations from. And in order to do this, I'm going to work with multiple data sets, including the citizen scientist observations, as well as ceilometer data and a few other tools. At the very end, we're going to run these cases with the new machine learning algorithm and see if it helped to clear up all this false cloud detection. So now I'm going to talk a little bit about the data sets that I've been using. The first one is the Globe Citizen Scientist Terminator dataset. And this was the one with the intense observation period. It released of March of 2021. And citizens could go outside using the Globe Observer app and make observations during the Terminator. And these observations would have to be an hour after sunrise, or up to an hour after sunrise, and up to an hour before sunset in order to ensure it is a Terminator observation. So again, what they would do, they would go outside and take photos of the cloud cover, and then they would report it, report cloud type, sky visibility, sky color, and other variables. And then what's really cool is that the citizen scientist observation is then matched with a geostationary satellite. So the citizen scientist will get an email that their observation has been matched with a satellite. And most of the time, if you're in America, it's going to be GOES 16 or GOES 17. And then the satellite's going to tell you what it sees. So it's going to report back to the citizen an infrared image, as well as a visible image, and what it thinks the cloud cover is total, and for high altitudes, mid altitudes, and low altitudes. So in total, this data set gave us about 500 Terminator observations in the United States. Another data set that we utilized is the larger globe data set. So what differentiates this from our Terminator data set is that the larger globe data set encompasses all of the observations that citizens have made, no matter the time of day. So what makes a citizen's observation a Terminator observation is if they add a caption to their photo and they type in Terminator. So if citizens are taking photos during the Terminator, but they're not including that caption, then we don't have access to that data. So we wanted to tap into that, and we used this larger data set and subsetted it for the times the Terminator was passing over the citizen. And this heat map here displays sort of the spread of where we got most of our observations. As you note, in Florida, that's a major hot zone. In near Langley, which is located here, we get a lot of observations, as well as this eastern Michigan and northern Ohio area. In total, there's 2,200 observations. This is all from this year in the United States. And lastly, I used a ceilometer data set. And the reason we used this data set was in order to check the citizens' observations from this larger data set I just explained. So the larger data set, citizen observations were sometimes more inaccurate than our Terminator data set, which is why we brought in the ceilometer to essentially check to make sure the citizen is accurately reporting cloud cover. So if the ceilometer and the citizen agree, then we can assume that that is the expected cloud cover of a sky. And then if the satellite disagrees, then that might be a problem. So what ceilometers do, they are these lasers, and they accurately measure the lower level cloud variables up to 25,000 feet. And one of the things that we did need to think about when using this is, say you have a scene of clouds where 100% of cloud coverage is in the mid to high altitudes. We might need to throw that case out because the ceilometer really can't accurately measure those. So that's just something we needed to think about and have in the back of our head when using this data. So these are all the ceilometer stations in the United States. There's a few that sort of leak into Canada and Mexico. But it's important to note that there is a large concentration near the areas I spoke of. So near Langley, you have a large you have a large amount of ceilometer stations. In that Florida area, in eastern Michigan, northern Ohio, there's a good amount. So that's good for us because that means we can match them with most observations. Ceilometer stations must be within 30 kilometers of a citizen's observation in order to match it with it. So we need many ceilometers is spanning a wide area in order to make sure that we're not throwing away citizen observations because it can't match with it. So there are ceilometer stations. These are the ones that are near NASA Langley. If you can see, there's a little red diamond here, which represents NASA Langley. And right next to it, there's a little circle, which is a ceilometer station. And that's very good because lots of our observations do come from Langley or around Langley. So if they're near it, then they will be matched with that ceilometer station. That was very reassuring to know that because we want to, especially the areas where there's a large concentration of observations, we don't want to be throwing those away. So having a ceilometer station right near Langley really did ensure that we kept our observations. So some of the limitations of these data sets, there's the Globe Terminator IOP dataset, which was the first one where citizens would type Terminator underneath their photos in order to add it to this dataset. We had about 500 observations, which is a large amount, but one of the limitations is we wanted a little more, which is why we tapped into the larger Globe dataset. But besides that, the Terminator dataset was very useful and the citizens were very accurate in reporting variables. And then the larger Globe dataset, that was one of the problems where some of the observations were inaccurate. So when I'm looking at satellite cloud cover and citizen cloud cover, if they're not agreeing, a lot of the times with the larger data set, it was because of human error, which made it time intensive to go through those observations. So that's why we had to bring in the ceilometer data set to make that process a little more efficient. But one of the problems with the ceilometer data set is, again, it can't detect those mid to high level clouds. And there can't be a ceilometer station everywhere. So when citizens are making an observation, like me at my house, if there's not a ceilometer station within 30 kilometers, my observation wouldn't be used in the larger Globe data set because we can't ensure accuracy with the ceilometer. So those are a few of the drawbacks of some of these data sets. So now I'm going to get into the approach and sort of how I utilize each one of these data sets in order to obtain the false cloud detection cases. So first, I know I've talked a lot about citizen observations, and some of you might not even know what that is or what a citizen observation consists of. So I wanted to give an example, and this right here is what a citizen would provide us with. So they're taking photos of the 4 cardinal directions, north, south, east, west, as well as up and down. So they provide us these photos in order for us to determine what the cloud cover is, and they report it as well. So this citizen, if you see in this green box down here, they reported few or less than 10% of cloud cover. And they also reported altostratus clouds. And I would say that's fairly accurate with the photos we're seeing. Of course, we don't have a full panoramic view or 360-degree view of the sky, but this is fairly close, and you can see some blue in the sky. So I would say they're within a certain degree of accuracy. So then the citizen is matched up with a geostationary satellite. In this case, it's going to be GOES-16. GOES-16 is one of the satellites that covers North America. So this is the same one we looked at previous. The citizen is in the middle of Oklahoma, and this is what they see when their observation is matched with the geostationary satellite. They get a visible image as well as the infrared. And in a visible image, down here you can see sort of a cloud sheet south of them, as well as some scattered clouds north. But where they're at, there doesn't appear to be much of anything. And then the infrared image sort of backs that up. You can see scattered clouds here or there, but there definitely isn't a lot if they are present. And then what the algorithm outputted for the total cloud cover was 98.47%, which is insanely high. Our citizens said that there was less than 10% cloud coverage where they were looking. And another thing that's sort of like, I initially thought that, okay, maybe there is 98% of cloud cover, and maybe it's just in the higher altitudes. Maybe you can't see it from the citizen's photo. But if you take a look at cloud cover based off of altitude, most of it is in the low altitudes. Approximately 95% of it is, which would mean they're easier clouds to see from the photos we're provided. And as you can see, I definitely don't think there's 95% low altitude cloud coverage. So then with all this information, we would then generate products that display this case. We already looked at this. This is the same case we looked at previously. But just to reiterate, as the cloud mask animation progresses and the terminator line passes over our citizen, it brings with it a band of false cloud detection. So right here is a great example. The whole Midwest essentially is covered with this false cloud detection. And the RGB image, you don't see a whole lot of clouds. There are some present, but just not to the extent our algorithm is reporting. And another thing that also makes it easier to see this false cloud detection is you see very unnatural clouds. So for example, here you see almost these boxes essentially of cloud detection, and that's not a natural formation by any means of clouds. And you almost see like a staircase right down here. So those are the things we're looking for when we look at these animations. So I took two approaches in order to identify the different cases of satellite false cloud detection. The first approach was using the Globe Terminator dataset. So initially, I would identify cases where the satellite's cloud cover disagrees with the citizen's cloud cover. And then I would look at that case, I would look at the citizen's photos and the other variables with it. And then if I found it that it was a useful case, I would then generate these animations in order to back up my point. And then once I record the cases where the satellite falsely identifies the cloud coverage, we would run the new algorithm on those cases to see if it cleared up any of that false cloud detection. This is a graph that I would look at in order to identify these cases. So what this graph is essentially doing is it's saying when the satellite is reporting a total cloud cover of 90 to 100%, what are the citizens reporting? So this whole graph encompasses the observations where the satellite is reporting 90 to 100% cloud cover. And this x-axis variable is what the citizen is reporting. This green bar here is when the citizen and the satellite both agree with the cloud coverage for the current scene. And all the red bars are when the citizen and satellite are disagreeing. I'm really interested in these last 3 or 4 bars because they have the largest discrepancy between cloud cover. So if a citizen is reporting clear skies at 0% and a satellite's reporting 90 to 100, that's a large difference, and that's worth looking at, whether the citizen is maybe misclicked or something like that, or the satellite is really widely falsely identifying cloud coverage. So this text box that I included on the right-hand side is an example of something I would have outputted into my terminal. I would output each one of these cases in the last few bars, and it would output the observation number, as well as the satellite cloud cover and the citizen cloud cover. And the citizen here, they're reporting less than 10%, so this observation would be within this bar. And I would use that observation number in order to find the photos that the citizen is taking and the variables they're reporting. So my second and last approach I took to finding these cases was using the larger globe data set. And I mentioned earlier how we would subset that in order to get when the terminator is passing through. And I was very vague. What we would actually do is use what's known as the solar zenith angle in order to find when the terminator is over a citizen's observation. And what this is, if you look at this figure here, the solar zenith angle is represented by the variable z. So when this angle is 82 to 90 degrees, the sun is very close to the horizontal plane, which means it's either a sunset or sunrise. So by using this angle, we can determine whether a citizen has the terminator passing through when they're taking an observation. As mentioned before, we would then just match each observation with a ceilometer station, and it needed to be within 30 kilometers because the citizen and ceilometer need to be close, so they're measuring the same area. And this did discard a good amount of data, but it was worth it because we could efficiently go through the data that we had. And then after we would go through all that data, we would again record the cases and at the very end, run the new algorithm on them to see if it helped improve cloud detection. This here is a graph of all the times ceilometer stations and citizens were matched. This right here, it may not look like there's a lot of matches, but that's because a lot of our citizens take multiple observations and contribute a large portion to our data set. So this, I think, is a better representation of what you're seeing. We have the heat map, where again, we do have the hot zones near Langley, Florida, Eastern Michigan, and Ohio. And that's because we have citizens who contribute a lot of observations in those areas, as well as some others. In total, there was about 162 matches with ceilometer stations within the continental United States. So I would use a similar graph as approach one in order to identify these cases. This one's a little different because I'm using the ceilometer total cloud cover instead of the satellite. So this graph encompasses all of the times the ceilometer station is reporting 0 to 5% cloud cover, and we're looking at, okay, well, does the satellite agree with it? So I would be looking at these three bars here, where the satellite is saying, no, the cloud cover isn't 0 to 5%. It is anywhere from 25 to 100, which is a large discrepancy. This, again, is an example of something that would be outputted in the terminal. This is representing the satellite cloud cover of 45%, and the citizen cloud cover is 0%. So what's important here is that the citizen is matched up with the ceilometer. So we're looking again at the cases where the ceilometer is 0 to 5%. And if the citizen, again, if they're saying it's 0% and the satellite's saying it's like 45, then that could be a case of false cloud detection because both of our ground observations agree. However, the satellite doesn't. All right, so now I'm going to talk a little bit about the results. In total, we found 5 quality cases of the GOES 16 satellite falsely identifying cloud coverage, and there were also a number of cases found for the GOES 17 satellite. However, they haven't been implemented yet. The new algorithm hasn't been implemented for the GOES 17 satellite, but in the future, we will use those cases to help ensure that the new algorithm is accurately measuring cloud cover. So at the bottom are the 5 observations, the 5 main ones that we took a look at. This total cloud cover percentage column is what the citizen is reporting, and this geo total cloud cover is what the satellite's reporting. So it's important to note, you do see these larger discrepancies where the citizen here is reporting less than 10% and the satellite's upwards of like 98. And it's also important to note that the solar zenith angle for all of these is essentially, most of them are within that threshold that we talked about of the 82 to 90 degrees. So now I'm going to get into what the new cloud mask looks like with our machine learning algorithm. So this is the case we looked at, essentially the whole slideshow, but there will be more cases as well. But I thought I should touch on this one. So initially, where a citizen is located in the middle of Oklahoma, there's a 99.53% cloud cover where they're at. And with the new algorithm, it didn't clear it up massively. It cleared it, it's still 94.39%. But that could be because of a lot of factors. the algorithm might not be perfect as of now, but also there could be clouds that we're just not seeing in the citizen's photo, and it's hard to tell at sometimes. But nonetheless, if we look at this new animation, the one on the far right here is the new machine learning algorithm, where the one in the middle is our old algorithm that we've been looking at. So as the Terminator line is passing through the Midwest, here's a great example. You see the whole Midwest covered with our older algorithm, and in the new machine learning algorithm, you don't see that, and you see a lot more natural clouds being detected. And some of this could be false cloud detection, but at the same time, there are clouds present. And while this new algorithm isn't 100% perfect, we're still working to refine it, and it is considerably better than the old Cloud Mask product. And I also wanted to point out the top right graph. What this displays is the solar zenith angle. So when it's between 90 and 82, we said it are the best cases. So 90 and 82 is this lime green color and sort of a little into the light blue. So where the citizen's located in Oklahoma, they took a quality observation. So this next case we're looking at is in southern Michigan. And with our old algorithm, it reported a cloud cover of 43.75%. And with the new machine learning algorithm, it cleared it up completely, and there's now 0% cloud cover. So the citizen is located where this pink square is, southern Michigan. And this is a sunrise case. So as the Terminator approaches, you can see in our older algorithm, this sort of faint line, which is all the false cloud detection. And as it approaches closer, it becomes more visible. And you can see this unnatural diagonal line that's essentially looks like a staircase. And in our new machine learning algorithm, our new Cloud Mask, you don't see that line of false cloud detection at all. It completely cleared all of the false cloud detection where our citizen's at. And as it continually progresses throughout the globe, you see, this is a great example. You see even in the Midwest, there's a lot of false cloud detection, where in our new example, you don't have any. So the last one we're going to look at is a case in northern Georgia. Right here, initially where the citizen is located, there's about a 47% cloud cover reported. And with our new machine learning algorithm, it's about 13.9%. So this could have cleared up all the false cloud detection. There could just be some low level or high level clouds that we're not seeing, but it cleared up most of it. And as you see in the animation, again, we have that sort of staircase looking line of false cloud detection. And as it goes over our citizen, you can see it in our old SAT-core algorithm, where in the new one with machine learning, you don't see that line at all. And it'll continue. In the Midwest, it seems to get really bad for whatever reason in our old algorithm, but you don't see that at all in the newer SAT-core machine learning. So the conclusions that I came to from validating this new algorithm is that the new algorithm does improve the ability to detect clouds from satellites during the Terminator compared with traditional methods. And another thing is that Globe citizen scientists, their observations, especially the ones in the IOP that were just meant for Terminator observations, they were very useful for identifying satellite cloud detection problems. And another thing I did note is that the larger Globe dataset did contain greater inaccuracies than the IOP dataset. And that's just interesting to note going forward when we do use citizen scientist data to solve problems like this. So some of the future work, the SAT core team will continue to refine this new machine learning algorithm as time progresses in order for it to be applied confidently to the other geostationary satellites. So currently, I believe they're working on applying it to GOES 17, and then eventually they'll apply it to Meteostat and the Himawari satellites. We're also going to continue to evaluate the impact of this algorithm in order to just ensure that it's continually detecting clouds at a good accuracy. Lastly, the detailed evaluation of satellite and citizen scientist data revealed inconsistencies in some of the ways citizens report certain sky conditions. And we were able to clean a lot of this data, and from the work that we've done with it, in the future, we can improve the quality of some of these citizen scientist observations. And it's also important to note that with this IOP, quality doesn't seem to be a problem where citizens are making accurate observations. So in the future, if we have a problem similar to this that we need to solve, then we can utilize an IOP as well, because in this case, it helped a considerable amount to solve or to validate the new algorithm. So my takeaways from this internship, I was able to actually apply a lot of my skills that I learned at Maryland. So I was able to reinforce some of my Python skills here. And I actually learned MATLAB throughout this internship. So I had no knowledge of MATLAB before, and I was using it a lot to work with these larger data sets and to produce some of the figures that you saw. So that was really cool in order to learn MATLAB from people who have been working with it for a while. And I also analyzed and compared data sets with different variables and formats. These few data sets I worked with, they were all different file extensions. They all had sort of like different problems when comparing them. So it was really nice to get that real world experience where it's not always easy to compare data sets where like in school they might make it seem like that, where you actually need to sort of problem solve and think about different ways to utilize multiple databases and data sets with this information. I also learned the process of how satellites detect clouds. Before this, I had minimal knowledge of satellite cloud detection, but I was able to learn like about ancillary data and how it's used to detect clouds, and as well as during the Terminator, especially how it's so uncertain with this false cloud detection. I use data analyses in order to determine the accuracy of data, and I also was trying to figure out how to make it more reliable. So I would say like the first half of my internship, this was like a big problem for me because I wanted to utilize the larger globe data set, but some of the observations were very inaccurate and I didn't know how to filter them out. So I did a lot of problem solving with members of the SAT-Core team and Globe Clouds team, and it was nice to be able to sort of figure that out and to problem solve. And you don't get that experience in school because, so it's nice to be able to actually think through these things and sort of get this real world experience. Another thing is that I was able to connect with colleagues from different teams all around NASA. It was great to be able to connect with everyone, especially in an online setting and not in person. My mentors made that very easy for me to connect with others, so thank you. Lastly, one of the pluses of working on the Terminator problem is you look at sunset and sunrise photos essentially all day. So these are just some of the cool photos I thought from going through them. One really cool thing about the Globe project is that everyone from all around the world is trying to solve a similar problem in a sense. So you have observations from like India, from Florida to construction sites, people on airplanes, and like this top photo here is from a schoolyard where students were making observations. So it's nice to be having all these people from around the world sort of contribute to the same problem. And it's really cool what everyone can do when we sort of work together in order to help solve a similar problem. All right, so I had a lot of people this summer help me, and I just sort of wanted to go through each one and say a quick thing about everyone who's helped me. First, I want to start off with Marile. She was my mentor, and essentially anything I needed, she helped me with, whether that's making connections or help with code. If she didn't know something, she would give me someone who could help me. So thank you so much, Marile, for being my mentor. Tina Rogerson, she helped me a lot with obtaining Globe data sets and the up-to-date Terminator data set and the larger Globe data set. So thank you, Tina, for helping me to make sure I always got the data I needed. Jason Wells, he helped me a lot. He was always in the meetings or any Terminator meetings I had, and he would always offer his insight, whether that's for my MATLAB code or just even career goals. He would always sort of lend his insight. So thank you so much, Jason, for helping me this summer. Brant helped me a lot in the beginning of the summer with sort of cleaning the Globe data. He would give me like certain cases where I could alter some of the data points that the citizens would report. So thank you, Brant, for doing that. Now on the SAT-Core team. Cecilia helped me a lot with like learning MATLAB essentially. She was my teacher for MATLAB. So whenever I had like a quick question, she would meet like that on a dime. So thank you, Cecilia, for taking the time to do that. Bill Smith is my other mentor, part of the SAT core team, and he would help me a lot with sort of making sure that I stayed on task and I was not going down a rabbit hole in a sense for a lot of times. So he would help me stay on track with my project and give me feedback on different things I was doing just to make sure that I was actually sort of continuing on this path to complete the project. So thank you, Bill, for mentoring me. And then where are we? So Doug, he helped me a lot with getting the salometer data. I think it was a few weeks ago I needed it, and he just got back from vacation, and he got me the data in like 2 days. So thank you so much, Doug, for spending the time to do that. And he's also getting me salometer data that I'm going to contribute to the my fire research program at the University of Maryland. So thank you. And speaking of that, Dr. Jones is my research mentor for the fire program, and she's helped me a lot. Well, without her, I wouldn't be in this position. She presented this opportunity to me, and she has prepared me for it with the research we've done in our stream. So thank you so much, Dr. Jones, for that. Will McKinney has helped me. He is the system admin for our directorate. And in the beginning, when I'm setting up my laptop and MATLAB and all that, I had so many problems, and he would meet with me right away and help me. So thank you so much for that, Will. And lastly, Jason, he was like my mentor that wasn't my mentor. So I was taking a summer class and we needed a mentor that wasn't for me, that either wasn't Marile or Bill. So I asked Jason, who's a part of the Calypso team, and he helped me a lot with trying to figure out what I was producing, I guess, with some of my figures, and also sort of going through the more technical aspect of my research. So thank you, Jason. And thank you to anyone I didn't mention as well. So many different people helped me this semester or this summer. So thank you for this great experience. Lastly, I wanted to plug the Globe Observer app. Some of you might have not been familiar with this prior to the presentation. So you can download this app on the App Store or the Google Play Store if you wanted to contribute to some of these problems. There's a ton of different projects, not just globe clouds. I believe there's some for like trees and mosquito habitats. So you can download this app, it's free, and contribute to them. Another thing is if anyone's interested in the SAT core and globe data, you can access them from these links. So this one on the left here is the SAT core products, and it includes all of the geostationary satellites. And then the one on the right is the Globe Observer website. So if you wanted access to the Terminator dataset or to the larger Globe dataset, you could access it there. Feel free to take a screen capture or just message me and I can send you the link. These are the sources for my code. And that is it. Thank you everyone for coming to my presentation. I appreciate your time. And if you have any questions, feel free to unmute or type them in the chat. Thank you.